Okay, guys, so let's do a couple of polynomial commands that I need you to, to really understand. They're going to be the following, okay? Yeah, perfect. So remember, guys, that the polynomial in MATLAB is considered as a vector, okay? So let's imagine that we have y equals 3x4 plus 2x cubed plus 6x squared minus x plus 5, for example. Okay, so this is a polynomial. So how do you enter this polynomial into MATLAB? For MATLAB, what it does, it counts from here towards this part here. Okay, and basically it's going to say, okay, the first number is going to be x to the 0, the second number x to the 1, etc. So for MATLAB, this is going to be 3, 2, 6, minus 1, and 5. Okay, now this is very important, guys, because imagine that you have the following equation. Okay, you have now 3x4 plus 2x squared plus 6. Okay? MATLAB, if you write this one here as a 3, 2, and 6, MATLAB is going to believe that it's going to be 3x squared, 2x, and 6. Got it? So what you need to do for MATLAB to enter this equation here, what you need to do is, okay, is 3x4, 0x3, 2x2, 0x, and 6. So this is going to be the way you're going to enter in MATLAB. Okay, so this was part of the recording that you have seen the other day. Make sense to you guys?
Yeah.
Okay.
Yes.
One of the commands that is really important, we're going to be using this quite a lot, is the command that is called polyder. So it is what it does, it simply takes the derivatives. Right? So let's assume that, let's call this one polyder is my command. Imagine, guys, that what I want is, what is the derivative of y respect to x? So in this case, it's going to be 12x cubed plus 6x squared plus 12x minus 1. Do you agree? This is my derivative. So this is exactly what polyder does. Okay, how this works. So let's call this, for example, h equals polyder of y. Yeah, so let's call this y. Okay, can you test this one here? And verify that indeed the result h is going to be then, guys, in MATLAB terms is going to be 12, 6, 12 minus 1. You need to enter this as a vector, guys, remember. So sorry, it's not parentheses, then here is brackets. Is 3 to 6. Three to 6 minus 1 and 5. Do you agree? So this is my y. And then I call h equals poly derivative y. No semicolon, just to see the result. And then we got 12, 6, 12 minus 1. Do you agree with that, guys?
Yes.
Okay, perfect. So now let's use another. So this is polyder. So there is another command, guys, that is extremely important. That is called polyval. Okay, how this works? Let's do this. Imagine, let's define x from 1 to 3. No, let's do perhaps a lean space better. Okay, I want to go from 1 to 3, and I want 100 observations. remember the link space, guys? Simply is like creates a sequence, so it's not semicolon. It's column. It's comma. So we want to create a sequence between 1 and 3, and we want 100 observations. Okay? And then I have my polynomial h. Do you agree? So what I want to see, and h is 1, 2, 3, is 12x cubed plus 6x squared plus 12x minus 1. So what I want to do is I want to see this polynomial. I want to see how this equation looks like in a graph. Got it? So that's why polyval is very important for that. It's extremely useful. So let's assume that I will call it, I don't know, h1. It's going to be polyval. What? So I have my function. My function is going to be h. And what values I will use? I will use the values of x. Got it? So it's basically like saying, replacing when x is 1, what is the value of h? When x is 1.001, what is the value of h, etc. Make sense to you guys? And now we can plot. So you can take a look to what happens. Plot of x with h1. So this is going to be my function. Make sense to you guys? You understand what we are doing? We are evaluating a polynomial. That's why it's called polyval. Now, let's do one example for you. So imagine, guys, so now let's assume that you have the following equation. So y equals x cubed plus 4x squared minus 7x minus 10. Can you plot this function, please? Evaluate this in x that belongs to the interval -1, 3. Okay, 1 minute to do this. Okay, so let's do this, guys. MATLAB. So I will define a new function y. A new function y equals, it was 1, 4, -7, and -10. Do you agree, guys? And then I can do my linear space now, the same linear space as before. But now it's between -1 to 3, and I say 100 values. That's okay. And then I can plot, sorry, I need to polyval. Let's call it h2. Polyval of y is my function, right? So remember here, guys, it's not an axis. Y in this case is a function. Is this function here. And I'm evaluating this function using the values of x that are defined here. Okay, so let's do that. And let's plot this one with h2. And my graph should be this one here. Do you see?
Yeah.
Perfect. Okay, so now let's move into a kind of related topic, but it's a kind of a different also. That is, we're gonna start working with polynomial curve fitting and linear interpolation. Okay. So let's talk about curve fitting. Okay, so I send you some dummy data set, guys. Can you please upload that? The first one. Let me check the first one. I send you this one here. Can you copy this one here? You have this in your email, guys. Can you please copy this here? So what we're doing, guys, is curve fitting is normally what we do. You know, we use different techniques for this one. We use, for example, the ordinary least squares. What we want to do is, in this case, I want to minimize the sum of a square of the errors, etc. The linear interpolation, guys, in the other point is different. Now, for example, let's see if I have points like that. Okay, when I try to do the OLS model, what I try to do is try to find a line that best fits these points here. So you're gonna have in between points. Now, when we talk about linear interpolation, what linear interpolation does is it considers every single point that you see in the data. Okay, and what it tries to do is simply try to see what is in between. Okay, for example, from this dot to this dot, what I try to do is, okay, so what can be the most likely values between these two values? Okay, with this one here, okay, what can be the values that are between these values here and these values here? So that's what is called linear interpolation. Okay, of course, we can use OLS, but we have another command, guys, that is called the polyfit. That also, the OLS is one particular case when this is a linear model. Okay, so let's use polyfit with this data. Go to MATLAB again. Let me move this one here. And so what we're going to be doing, guys, is let's assume that I call P is going to be equal to polyfit. What I want to fit, I want to fit X, the new X that we have created, and Y, and you need to add the degree. So I want to use, let's assume that I want to fit a quadratic polynomial. Okay. So these are going to be my values of my quadratic polynomial. So this implies that the data that fits this data here, okay, sorry, my model that fits this data here is going to be 9 minus 9.8 x squared plus 20x minus 0.017. Okay. Let's try to plot this stuff here. So remember, I have a polynomial, and the best way to see the graph of this polynomial is simply creating x. So let's do xi, and let's assume that this is going to be, let's do a link space 0 to 1 and 100 values, just very small. Then I can do my z. Let's do polyval, what we have done before. What is my function? My function is p. What are the values that I want to fit with xi? Okay, and then I can do a plot, and I will do a plot here just to let you see how this works. I will do xy, the original xy. I will do this with circles. Then I will do the xy, just the common plot, the lines. And then I will do my xi z, that is my fitted function. And this my fitted function, I will do dots. No, not this one. Okay, so what I'm doing is I'm graphing X and Y, the real data. I'm just putting a dot, so it's not going to be a line. And then I'm doing X and Y. Now remember, the X and Y regular is simply a line. And then I finally will do my XI with Z, and I will use dots to check this. So let's take a look to how this looks like. Oh, where's my graph? Here we go. Do you see, guys? You don't see this very clearly. We can change the colors. But you see the dots here, guys, represent the real observations, the XY pairs. Now, if I do the plot, what it does linear interpolation. You can see what it's trying to do linearly is what is the more feasible value between this point and this point using a line. What is the most feasible point from this point to this point using a line? And you don't see this very well. Can you see the orange dotted line here, guys? That looks
Yes.
like a quadratic function. Well, it is a quadratic function. So this is my polynomial fit. Got it? And so that's the difference. So the polynomial fit tries to do something. In this case, what we're trying to do is trying to minimize the sum of the square of the errors. Okay, there are several other criteria. We can try to minimize the Frobenius norm, etc. But that's the idea. Make sense? So linear interpolation is this, and my polynomial fit is like a more smooth function. Okay, so now we can do also, guys, let me minimize this one here. Let's create another another polynomial. Let's assume now that I want p. Where's my p? Instead of 2, I just want 1. So what I'm doing is I'm trying to fit a line. So this is a typical OLS model, guys. Okay, so it's going to be 10.31x plus 1.44. Got it? So let's do another z. I evaluate this one in my new polynomial. I will do a hold on just to show you what happens in the graph. And then I simply I will plot my xi with z, and I will call this, yeah. Oh, sorry, what I've done. Oh, no, that was good. Yeah, so we can take a look to what happens here. You see my line? I did the blue line in this case. And the blue line follows the simple OLS model, okay? Remember, guys, that also that the quadratic can be an OLS model. The only condition that the OLS model has, guys, is that the coefficients should be linear. But the data can be a square, can be a cube, can be whatever you want, okay? So what I mean is the following. When we have the OLS model, guys, we have a linear assumption, okay? So my OLS model has the linearity assumption. Linearity assumption. So the linearity assumption, basically, you cannot confuse these ones here. Imagine my model is going to be this plus an error. This is correct. But also a linear model, guys, can be the following: a plus bx plus cx squared plus an error. Do you agree? So what the linearity assumption tells you is that these coefficients needs to be linear. Makes sense to you? So that the model below belongs also to the OLS model because it's simply the data is square. No issues with that. It is perfectly feasible to continue using the OLS model. Okay, questions about the polynomial fit, guys? One issue that we have always when we try to do curve fitting, guys, is you can see that the line is okay, but apparently the quadratic function is better. Do you agree? It's better capturing this type of curvature that the data is showing. So one of the problems that we can have here, guys, is that we can perhaps overfit. So what is overfitting? So let me do the P. Yeah, this one here. So I will call this PP now, okay? And now instead of using degree 1, I will use degree 10. Just to exaggerate. Okay, so I will have a 10th power polynomial. So I will do my Z my Z was this one. So I will call this ZZ. And I want to evaluate my polynomial is going to be degree 10, xi. And then I will plot. Yeah, let me do another figure. Otherwise, it's going to be too confusing. Figure, and let's do a plot. I will do xy again with dots. I will do the, and then I can do the XIZ, the previous one that is a line. And I will do this perhaps like that. And then I will do XI with my ZZ. And it's going to be a straight line. Oh, yes, of course. Z. Now we have it. You see, guys, what happens? So this is overfitting. You know, it really damages your analysis, because from this point to this point, instead of having a linear interpolation, you can see a linear fit. This makes huge, kind of a weird movements. You see, this is the problem with overfitting, guys. So you need to be very careful about the selection of the degrees of your polynomial. Normally 1, 2, and 3 are at the most used in economics, okay? Now, if you go to neural networks, programs, etc., then you can use a higher degree polynomial. But in economics, 3, the cost function in economics, we normally know that it's a cubic function. You know, utility functions are quadratic, and OLS models normally work with linear data, okay? Make sense to you? Make sense to everyone? So be careful with this stuff that is called overfitting. Make sense to you? Are you there, guys? Yes. Okay.
Yep.
Okay, so now let's do some linear interpolation. So how linear interpolation works? Let's create two variables. Let's create x1. Let's do x1 to be equal to linspace. Let's say 0 to 2 times p, pi, and 100 observations. So let's work with some cosinus function. And let's define x2. I will do the same, but I will do only 6 observations. Okay? So let's do some plotting here. Because linear interpolation works, guys, when you have more points. Because the distance between points is smaller, so the linear interpolation basically makes more sense than having 2 points that are very, very far away that you don't know what is going to happen in between. Okay? So let's do, for example, x1. Plot x1. Oh, what's going on here? Yeah, plot x1. I will do the sine of x1. I will use the sine function. And I will plot x2 with sine of x2. Just to differentiate this one here, I will do. So I'm plotting x1 and sine 1. The sine function is the same, but the number of observations is different. So you can take a look to what, oh, sorry, I need to delete this one here. Yeah, you see, the blue one corresponds to 100 observations. The red one corresponds to only 6 observations. So that's why when we have when we're going to use linear interpolation, guys, what is better is to have the more data you have, the better. Got it? Questions? So let's do a couple of other things here. Can you please also go to your email? I sent you another data set. Hours and temperatures. Can you copy this one in here? So let me delete this one here, and let me copy these two guys here. You tell me when you're there. 1 minute, guys.
Do we need both or just the hours first?
No, both. Both of them.
Okay.
Hours and temperatures. Just copy both of them, and you're
okay.
gonna have them. So let's plot. Let's take a look to how this looks like. Let's plot hours and temps. And I will call it, and I want also to check hours and temps. What I want from here is just to identify the points. Okay, so this is my data, guys. I have hours and points, so I have my linear interpolation and I have the real observations. You see? So this is really a real interpolation. So plot, indeed, what it does is it interpolates. That is what it's doing. Now, the command for doing interpolation, guys, is called interp1. Interp1. This is the command that does interpolations, linear interpolations. So what I need to interpolate, what I want to interpolate, well, I want to interpolate hours and temps. I just need to give it an hour. So for example, what is the temperature between, what is the temperature, what is the linear interpolated value at 9:30 or 9.3? Okay, so let's take a look. So the temperature is going to be 22.9. So let's take a look to the data, real data. Where's my data? Oh, here we go. So 1 to 3, hours 1 to 12. So that the ninth hour should be around this one here, right? 12, 11, 10, 9. Yeah, so it's basically between these two values. Do you see? What is my interpolated value? In this case, 22.9. What I can do is also I can interpolate not only on a single value, but I can interpolate on an interval, on a series of values. So let's assume 3.2, 6.5, 7.1, 11.7, and then you have your interpolated values. Now, there is something that is special when we do linear interpolation. There is something that's called the cubic interpolation or the spline. Okay, so it basically makes more, it doesn't go a straight line, but it tries to fit a cubic function in between 2 points. So it smooths better the function. And it really works, guys. When I use the splines, normally works much better than linear interpolation. So it's very simple. So what we add at the end is simply a spline. And then you can see the difference. 9.3 linear interpolation is 22.9. When you use a spline, there is a slight difference, but it's a significant difference, 1 centigrades. This is all Celsius, okay? 21.85 centigrades. Okay, we can do the same when we have a vector of values that we want to do. We simply do a spline. And here you go. So remember, guys, this is so what I can do now is let's do a plot. Okay, so let's define my h equals, let's do from 1 increasing 0.1 to 2 to 12. Okay. Oh, I should have done that. Yeah, and then what I will do is I will say t is going to be my interp 1 hours temps. I will use h. So instead of having 10 values or 5 values, I'm using 111 values. And I want to use a spline. I don't want to show the values. Now, just take a look to what happens. So let's plot hours, temps. I want h and no, so I have hours and temps. I can use here. Then I can have hours and temps. And temps, just the regular values.
Professor, I think the screen is frozen.
Oh, no, I haven't said. Oh. Yeah, guys, where were you? Yeah, we did this interpolation, do you agree? So I can have a vector of values, and I can use the spline. But instead of having a vector, I want to have something more continuous. What I will do is I will create a variable h that is going to go from 1, increasing by 0.1 up to 12. This is my variable h. And then what I want is I want to interpolate. I want to use the data, hours, temperature, use H, that is my data, the points of interpolation. And I want to do this as a cubic spline. Now, what I will do is I plot, hours and temps, just the dashes. Now, hours and temps, just to identify the exact points. And then finally, I will write H and T. That is my linear interpolation. So here you go. Take a look. So my linear interpolation, guys, is the blue, dash blue. The actual points are the crosses. And my cubic interpolation, guys, is my orange continuous line. Do you see? It really smooths the data. It is fantastic also for what, guys? For derivatives. Remember that what is a derivative is simply the slope at a given point in time. Do you agree? Now, if you find the slope in this point here, it's infinite because there is millions of possible slopes here in a point. But if you take the curve, you can have the slope, that beautifully slope. You can estimate the slope very easily. So that's why in economics, guys, what we try to do is we try to smooth the function. Okay, I will show you that later, but that's what we try to do. And splines really help us with this. Make sense?
Yes.
Perfect. So now, guys, let's go into something that is related also. That is going to be is optimization. Yeah, we're going to be talking now about optimization. So let me clean this part here. Let me clear all this part here. Okay, guys. So what we're going to be doing is optimization, but there is one command that is beautiful. Let's do the following. The name of the command is fplot. Okay. I will use this one here. The name of the function is an example from MATLAB. Humps is a function. Okay. So what I'm saying is, please, fplot tells, okay, use this function that is called humps, and in this interval, and plot it, comma 2. Here we go. So fplot, guys, uses pre-functions, functions that you can create, and you just give them an interval. Okay, let's do another one that we can create by ourselves. So you have created, this is fplot. Take a look to fplot. We're going to work with this fplot. It's just a function created by MATLAB. Okay, so now what we can do, guys, is we can do another one. And so what we do is always we tell MATLAB, what is my variable of interest? My variable of interest is x. Okay, what is going to be my equation? I don't know. Let's do 2 exponent of minus x. I'm just creating a function, guys. Product sine of x. And I want this to be plotted in the interval 0, 8. Okay, so I really, unfortunately, I discovered MATLAB later after I was in the university. Sometimes when you start working, guys, when you do economics or this type of analysis, that the professors always use functions. You agree? Okay, let's do a quadratic function, let's do a cubic function, but I had no idea how the function looks like. Okay, this fplot helps you just visualize the function. Do you have an idea how this function works here, guys? How is the shape of this function? Do you have an idea? Just by looking at the function. It's a mixture of exponents, so it's negative, so it's going to go from a very high number to a low number, perhaps, and then we have a sinus, so it's going to have some volatility. But it's very tricky to imagine. Do you agree?
Yeah.
Okay, and then in here, what's going on here? 2 times, yeah, perhaps now this is a new version of, let me check, this exponent of x, sine of x. I'm not sure if they are changing this one here because I know there have been changes here. Okay, let me check why it's not responding. So, okay, so if plot at x, 2 times exponent minus x, let's do times sine of x. Yeah, so what was the first complaint? Check for missing multiplication, missing, okay, so let me check. F plot, my command is correct. So this one blocks with that. Yeah, should be. Okay. Choose brackets and says the parentheses. No, 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 no. Okay, so let me check something. What I will do is I will call this F. Okay. And then what I will do is I will use F plot F. Yes. Yes. Okay, so let me check this one here. Oh, yeah, I know. So why? Wait a second. So, this is weird. But okay, MATLAB is telling me that this is a new version. Yep. So guys, this is the new way of doing that. Is add x, but x should be in parentheses. Okay, and then you write your function, and then the values that you want to basically the interval in which you want the function to appear. Okay, so this is the one, guys. So let's take a look to what happens. So this is the function that appears. Make sense? So it's going to be f plot add parentheses x space and the function. So we can do another one. F plot of x, for example, I have a function, let's do x to the power 2 minus 2 times x plus 3. I'm just creating any function. And let's do in the interval 0, 3, for example. Oh, sorry, I need to delete this one here. X to the power 2. Here we go. Yeah, this f plot has changed the denomination, guys, but in any case, it works. Okay, f plot is useful. You're gonna see later when you want to see, just in your career when you have a function and you want to have an idea how the function looks like. It has a maximum, it has a minimum, it changes signs, it crosses zeros, whatever. You can basically use a f-plot in a straightforward way. F-plot, you define your function and then you simply run in the interval that you want. Make sense to everyone? It's a very, very simple command that really helps a lot. Questions, guys? So now we have, guys, we enter into the world of economics, well, finance also, something that we call optimization. Okay, and for optimization, guys, simply it is basically in a given interval what is the maximum value of a function, okay, or what is the minimum value of a function, etc. So we're going to use three MATLAB functions. One of them is simply f min altogether bounded. Okay, this works with a single variable. So it's able to find the maximum or minimum of a single variable equation. or function if you want. Then we're going to go into something more complex. That is going to be the F-min search. Oh yeah, in a given interval, in a given point, let's call it. Okay, the F-min search, guys, works with multiple variables, and this requires something that is called the starting points. Starting points or starting values. And then finally, we're going to see something that is called the F0 function. That simply tells you when a function crosses 0. When a function changes sign. So meaning crosses 0. Okay? And let's do this using the functions that I gave you the other day, guys. I gave you, can you open this function? Let's do FMP mounted. I opened somewhere around here, I believe. Yep. Can you open this file, guys, that you have, that I have sent to you? It's called xfminbounded2.m. Can you open that and tell me when you have this open? This function here calls two functions that we have created. One that is called find underscore y minimum 1, is this one here. What it does is simply takes the value of x and replaces the values of x and returns the function y, or the value of y. Okay. Tell me when you have this function in front of you.
Yeah.
Okay, so a couple of minutes, you analyze, run the program, and try to understand what we're doing here. This is your function. You know this function, 2 exponent to the minus x sine of x. I deleted my, I think this was, so this is the function. Okay, and I want from you guys, what we want to find is what is my minimum, is around here, right? What is my minimum value and what is my maximum value? Got it? So that's all what we want to do. I want to know exactly where the maximum value in terms of x and y, and what is the minimum value in terms of x and y. This is what this function is doing. Can you please take a couple of minutes? Give me 1 minute. One more minute, guys. Run one line by line, understand the code. Because the goal of this class, guys, is you to learn how to read the code. Okay, not tomorrow, on Wednesday, we're going to do a lot of economic examples and we are going to run. And you're going to see that if you know this part that we have done, you're going to understand everything. And you're going to be able to create your own programs in a very, very quick, efficient way.
Professor,
Yes.
can I ask an unrelated question to the
Yes.
program?
Yep.
So you said next class is our last class and we have the project.
Oh yeah, I will talk about that on Wednesday. Yes, for sure.
Okay.
But don't worry, don't stress about that. Just stress about learning what I'm teaching to you.
Okay.
You're gonna see on Wednesday how beautiful and easy you can create your own programs. I will show you that, guys.
Okay. Thank you.
Okay. Just be sure, guys, that you have assignments number 1 to 6. Okay, that you have done them correctly and that you have sent this to me. On the weekend, I will be working on reviewing all of them. So please be sure that you have them. You have given this to me by now. Okay, so let's continue. So take a look to what this function is doing. So I'm defining my function. Okay. Then I do my float just to take a look to what this is doing, how the function looks like. I have done this already here. So I know that it looks like this. Then what I'm doing is I'm finding the minimum using this command, fmin bounded. Fmin bounded, what it will do is, remember, fmin bounded works because I only have x, a single variable, using the function and in which interval between 0 and 5. That's what xmin bounded is doing. So let's run up to here. Let me close this. Let me close this one here. Let's run up to here. Editor, run. Yep, we see the function. And you see my minimum. My minimum value is found in 3.92. You can see 3.92 is around here. Agree, guys? Okay.
Yeah.
Then I need to find that I have x, correct? I need to find y. So what I do in regular algebra, guys, what I do is I replace my x value on my function, in my function, and then I return my value y. I'm doing this one here using a new function that is called find y min 1. Okay, it's calling this function. I just do it. I should have done this in a single line, but it doesn't matter. I did this for you, just to see that you can call another function. What you do is you input the minimum value that you have found here, and what you're gonna get is your y minimum. Agree? So it will go here. Your 3.92 is gonna come here. It's gonna replace the values of x, and it's gonna return y to you. So that's what it's doing. Okay, so if we run this one here, this part is really, you need to move somewhere. Yeah, let's continue here. And then you have, take a look. My minimum value is found in 3.927 and minus 0.0279. So basically, we are around here. Make sense to you guys? Now, one thing that you need to remember is that all the functions, all the optimization functions in MATLAB, R, Python, or whatever you can imagine, are always in terms of a minimum, okay? But now, what happens if I want to find the maximum? Well, that's easy. Remember that the function, the negative of a function, is the opposite of a function. So if I'm talking a function that looks like this, okay? So what I can do is I can simply put a minus negative to all the function, and the function is going to look, this part, that the maximum is going to look like a minimum. And then I can find the minimum, and then you know that this is a function. Okay, so take a look to what happens. I will create another figure, blah, 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 blah. I will go up to here. Take a look to what happens when we do the minus function. You see? It is the mirror image of the function, guys, but now instead of having a maximum, I have a minimum. Then as soon as I have a minimum, then I can apply my if min bounded, if min search, if min search. I can do that. And then I do the same. I do my x max is going to be found using fmin bounded. My function is fn is a negative, you can see here, between in the interval 0 and 5. And this optim set, guys, simply allows you to see the iteration. Sometimes when you have a complex optimization, you want to see when and you want to see if your optimization is going into the right direction. Okay, let's take a look to what happens here. So let me run everything and take a look to what happens. Look, these are the optimization procedure. So it's one by one. MATLAB is going to tell you, iteration by iteration, is finding and is telling you, this is the golden rule, parabolic optimization, etc. And I arrived to this that is going to be my answer. Okay, so basically my maximum is going to be when x is 0.78 and my y is 0.6648. So let's take a look to if it's true. The maximum of x is going to be around here. That corresponds more or less to a 0.78, no more or less, corresponds to 0.78 and 0.64 value of y. You see? This is the way, guys, in which you can find minimums or maximums of given functions. We want to maximize utility functions, for example. We want to minimize the cost functions, etc. So you can do that with this function here, f-min bounded. The limitation of the f-min bounded, again, guys, is that it works only with a single variable, x in this case, x or y or whatever you want, but a single variable. Unfortunately, in economics, guys, we don't work necessarily with a single variable. We work with several variables. Okay. In this case, you cannot use the f-min bounded, but what we use is something that is called the f-min search. Can you open your example f-min search.m, please? Two minutes to analyze this function. Okay, guys. So let's take a look to how this works. The function x-min search basically allows you to work with multiple variables. In this case, my function is going to be defined in three variable function. It's x squared plus 2.5 sine of y minus sine z squared x squared y squared. Okay. What is tricky here, always in optimization, guys, is starting values. Okay, I'm given these starting values because I know this function. And then what I will do is I will find A. A is going to be a vector, a three components vector. I'm using f-min search because it is a multiple variable equation. I'm using this function. So this is the way you tell MATLAB where to look at. Okay, look at the 3-bar. This is the name of the function. This is my 3-bar function here. And use the starting values of B. So MATLAB, what we will do is we'll run, optimize, and then determine what is the B. So let's run this one here. You see? This is the value. These are the values of A. So A is going to be 0 for the first component, 0 for X, 1.57 negative for Y, and negative 0.4 for Z. Now I want to see what is the value evaluated at this function. What is the function evaluated at these values? Then I have created another function that is called eval fun. So I enter the vector A, it decomposes into components, and then simply computes the function. What is the maximum value and return C? So if we do that, we continue running. Here we go. So this is my optimal parameter values. And if you evaluate these values in your function, your minimum function is going to be at minus 2.5. We're going to do more with fmin search because that's the one that we use all the time, guys. Okay, so now let's go to the last one, is when a function crosses zero. Okay, and the function that is going to be using is going to help us to work with that is a function f0. Can you please open your example underscore f0? I also gave you this in the email. 3 minutes to analyze this function, guys. It has a lot of information. Can you please analyze this one here? Do line by line and understand what we're doing. Line by line and understand what we're doing. 3 minutes, guys. One more minute, guys. Okay. So let's continue. So remember, guys, that the function sine of the sine function looks like, where's my mouse? Here we are. So the sine function looks like this. Do you agree? So this is 2 pi. This is pi. This is pi over 2. This one here is 3 pi over 2, etc. So This is 1. And this one here is -1. So what we are trying to do is we're trying to find what is the exact value when this function crosses 0 degree, or when the function changes of sign. So here the function is positive, changes to negative. Okay, so that's the idea of F0. F0 helps you find these values in given enclosed by intervals. So let's go and see what we're asking for. So let's delete this one here. Okay, so I'm saying, please use the F0 function, use the sine function, and tell me what is the value when this function crosses 3. Let's do up to here. And you can see 3.1416. Do you recognize this value? It's pi. You see, so the sine function crosses 0 at 3.1416. That is a value close to 3. So now the F0, guys, you need to be very careful, because this is the tricky part of everything, is to find the values that are very close to give F0 a value in which really there is a crossing of 0. Now the cosine of a function, guys, looks like, so the cosine function, so this is my sine function. My cosine function looks like this, okay? So like this. 2 pi, and this is my cosine function. Got it? So now what we're trying to do is trying to find a value of the cosine in this interval, 1 and 2. Is the cosine crossing 0 in this interval? So let's take a look. At 1.57. 1.57 is pi over half, half of pi, right? This one here. This one here is pi over 2. So at pi over 2, the cosine function crosses 0. Yeah, I can do the F plot. Okay, so let me go here. Now I have, guys, a function that is a cubic function. So this function in economics is very similar to something that is called the total cost function. Okay, so what I'm doing here is the following. When I do at f, so this implies use my function. My function is defined not in here. My function is defined somewhere here. You can see here, here's the definition, the function f. And the function f is this one here. It's a cubic function that you saw in the graph. And I'm using basically f plot to quickly and easily take a look to the function. So I know that I'm talking about this function here. Okay. Now, what I want is to find what is the value of f. The function crosses 0. Where exactly close to the value 2? We do this. Here we go. At 2.04946. So let's take a look. 0 is around here. So basically crosses around here, 2 point something. Make sense, guys? It is in between these 2 points. And then finally, sometimes we have a function that is, for example, this one here, cosine of 2a or 3a, whatever. But I don't want to maximize on a. A is a constant. What I want to use is k as my constant, k as my variable. So what I will do is I will do the figure. I do the f plot. No, my variable is k. And where this k goes, okay, look for my function where I include k and a, and just graph in this interval, 0, 4 pi. So let's do this up to here. And here I have my graph. So basically I have what is that? A cosine of 2a. Oh, sorry, of 2k. So it looks like this. Now what I want to find is give me the value of k when it crosses 0, at around 0.1. That's all what I want to know. So let's run this one here. Here you go. This function crosses 0 at around 0.1 in this value, 0.7854. So basically 0, this point here, go down. It doesn't want to go down. In here, this point here is my 0.78 when it crosses 0. Make sense to you guys?
Yep.
Yep.
Okay, perfect. So before going to more examples, let's finish a couple of things that are useful. Let's do integrals, okay? And let's do derivatives that are always useful in economics. Integrals, we use this a lot, guys, in probabilities, you agree? What is the probability between this value and this value? So we use integrals. And derivatives for everything in economics, everything that is marginal, we use derivatives, okay? What is my marginal cost? What is my marginal utility, et cetera, et cetera, et cetera. Got it? The way in which we do what do you call integration is straightforward. It's very simple. So let's define x, for example, guys, between -1, increasing by, let's do 0.17 to 2. Just any variable. So let me move this. So I'm creating this variable x. I want to know what are the values of y evaluated in a function humps. Remember the one that I have used? Humps is a function. I want to evaluate the value, this function here on x. And let's do an f plot here. I want f plot humps in the interval. Let's do is -1 and say -1 and 2. Oh yeah, we can use indeed the new version is going to be, yeah. This is the new version, guys. This one here, forget about that. This is an old version. This is the correct way to do that. Okay, so you can see the function. So now what we are going to do is I want to find the area below this function. How do we do that? Well, let's call it area. This is a name, okay? And the command is trap Z and simply enter the function. So what is the area below the curve? Is 25.9172. Now, how the trap C works, guys? Okay, copy or take a look. The trap C works in the following way. So allow me 1 minute to save this one here. What we have done in this slide, guys, remember? Oh, polyfit. No, we have done polyfit. What we have done in this slide? Oh, no. Curve fit and linear interpolation optimization. Okay. So now I can do new one. Okay, in the new one, guys, how the how do you call it? Integral works. The trap C works in the following way. So imagine if I have, imagine this is my function, okay? I'm not sure it looks like that. But what we do is we create rectangles next to that. So we create a rectangle here, we create another rectangle here, etc. So in this part here works very nicely, do you agree? But if I start doing rectangles here, you see that there are some mistakes with this procedure. Is that this part here is it is not part of the function. It's not below the function. But also there are some parts here that in which you miss parts that are below. So and that's a problem with the trap C. The trap C, then how do you solve this issue in some way? Is you increase the number of intervals, because the smaller the intervals, the smaller the rectangles, and so the probability that you're going to be overrepresenting or underrepresenting the values are going to be lower. Okay, and that's what I want to show you here. So take a look when I have used 0.17. So now define x. Okay, but let's define x larger intervals. So let's do 0.07. Let's take a look to my I need to evaluate my y, and I need to do this one here. I'm sorry, I want the area. I want to have this one here, x and y. Take a look. You see the difference? So the larger the interval, the less precise our trap C function. Right? So that's why when you do integrals, simply increase the number of intervals, increase the number of observations in your interval, guys. So your calculations are going to be more precise. Got it? This is with the trap Z. There are two commands that are very useful, and they really rely on what is the concept of quadrature. So basically, the quadrature tells how, if we are in a flat part of your function, it's okay to use very, very fat rectangles. But when you have, curvature, very strong curvature, then you reduce the number of the size of the distance of the rectangles. So, I'm tired today. So basically, what it does is the following. So let's take a look. Let's assume. Let me do another graph, something similar. So I will have, I will do this flat first. It goes up, something like that. And then perhaps goes flat. So basically what this method does, if it's flat, okay, you can use a rectangle like that. Very careful, no issues. But if you have starting going up, the curvature increases significantly. So your rectangles are going to be very thin, very, very thin. So what do you do that? Why do you do that? It's basically because you want to avoid overfitting or underfitting. Got it? So this is the concept of curvature, of quadrature. And what is you don't need to worry about that. MATLAB is going to do this for you. So what I will do, guys, is I will call area 1 and it's quad 1. Let's do humps between -1 and say 2. Oh, it's not. What? So what is going on here? Quad. Okay, let me check. Yeah, this change of version, guys. Give me 1 second. So everyone, quad. Oh, I know. It's a comma missing here. So it is quad 1, guys. It's quad 1, yeah. Yeah, it's quad L. Okay, QUADL. Then you do the function, and then you do from where to where you want to estimate your how do you call it? Your integral, your area. And says you can see the difference. 25 versus 2634. So this is more accurate. It's also faster, guys, because it uses very fat rectangles when it needs, and very thin when it doesn't need, when it also needs. So it is very efficient. It's a very, very good way of computing this stuff. So integral is easy. So we have trap C and we have quad L. Okay, so this is an L. So these are the two functions that we use here. Now, integral are easy. Integrals. Now, when we do derivatives, guys, that's the tricky part. So let's take a look for 1 second. I don't know how familiar you are with utility functions, guys. Are you familiar with utility functions? Guys, are you familiar with utility functions?
Yeah, a bit.
Yeah. Okay, so basically a utility function of one variable x. Okay, let's assume this is water, and this is a utility that water provides to you. So normally a utility function looks like this. So this implies the following. When you don't have water and you drink a little water, the utility function for you is very high. Do you agree? But then you continue drinking water, you continue drinking water, you continue drinking water. So basically, every time that you drink a little more water, the utility of this little more is less and less and less. You see this quantity here, this height here, is very, very little compared to this height here. Okay, so this is a decreasing, this is the decreasing marginal utilities. That's what it's called. Decreasing marginal utilities means simply that every time that you drink something more, this something more creates less utility for you. Got it? And eventually, guys, this utility can go down. So if you continue drinking water and drinking water, so eventually you can die of drinking too much water. Make sense? So this is the utility function. Now, when I tell to you the marginal utility is decreasing, so this implies basically, guys, that your derivative at this point is like that. Derivative at this point is flatter. Derivative at this point is even flatter. And derivative at this point is 0. Got it? So, and if I graph this one here in terms of x and what is called marginal utility of x, what I expect is that the first one is going to be very high. Let me do a line here just to align my line with this one here. And my marginal utility is going to be like that. It's a line. Should be a line. I don't know. It's not a line. Definitely it's not a line in my graph. Should be like that. At this point here, value of x, I don't know how many liters of water, your marginal utility is going to be 0. So basically, you're going to be at this point here. After this point here, you start talking about this utility. It's not good anymore for you. It's bad. Make sense? So let's try to do this. How do we do this stuff? How do we do this stuff? Can you please go and open? Can you open again I think we have it. Yeah, I gave this to you already. Just let's call this back. This one here. Can you please again call this one here into MATLAB? Can you please do a polynomial fit of degree 2? So this data, guys, the data that you have there looks really like that. So what I want from you is to do a polyfit degree 2. So I want you to basically, your polyfit degree 2 is going to look like that. And graph that. Do the polyfit and graph. Okay, 2 minutes to do that. This is what we have done, perhaps 1 hour ago. 2 minutes, guys. Yeah, just to all go in the same way. Let's evaluate this into 0 and 1. Into 0 and 1. 100 observations. Two minutes. One minute, guys. Okay, so let's try to do this stuff. So I have X and Y. I can call it P. So what I want is to create a function that defines this data. Okay. So let's do a plot first. Just take a look at what happens. Plot X and Y. And I just want process. So this is my data, guys. You see? I want to fit this data, a polyfit. So what I will do is I will call this, let's call this P. P is polyfit. What is my function? My function. No, sorry, it's my data is X and Y. And I want a polyfit degree 2. Okay. Just to show you the equation. So this is my equation. It's going to be minus 9.81 x squared plus 20x minus 0.03, nothing. Okay. Then what I will do is I have my function. I want to evaluate this function. I told you, let's create in this space between 0 and 1, and I want 100 observations. So the default, 0 and 1. Remember the default, if I just enter two numbers here, the default is going to be 100. And then let's do my z is going to be equal to polyval. I will evaluate my function is called p, in which values xi. And then just to take a look, let's plot this one here. Let's plot just your xy, your data. Let's do this with circles. Let's plot x and y to do the linear interpolation. And let's plot xi and z. And let's do this, perhaps. And here we go. So my orange line is my fitted values, my data, and my interpolated values. Okay. Now, the orange one, that you don't see this very well, is basically this function here. Okay, this function here. So what I want to find is this function here, the marginal utility of x. So what I will do then, so remember at the beginning of the class, guys, we use one command that is the polyder. Do you agree? So what I will do is, before finding anything else, I need to find the derivative of this function. PD is going to be equal to polyder of P. This is the derivative of this one here. And here we go. And then now I can do, let's do CI. It's going to be polyval. I want to evaluate this one here. My function is PD on XI. And then I want to plot my XI with Z. Or CI, XI with ZI. Take a look to what you have here. Do you see? This is exactly what we want here. Make sense? So in economics, guys, what we do is first we find that the fit. We want a function that is smooth, because when the function is smooth, we can find derivatives very easily. Okay. One of the things that the people make mistakes is they try to use the values, these values here, to find the derivatives. Okay. And I will show you what happens if you try to do that, guys. It's a catastrophe, you're gonna see. So let's define dy. Remember, dy is simply I take the difference of y, and I simply divide this by the difference of x. That's all. That's the concept of a derivative. Changes on y when x changes. That's it. Okay, so let's do xd, for example. I will do simply the size. Should be 1 to length of x. And I need to reduce 1 just to make it conformable. Yips. Okay, so now I will plot my data and my. Take a look, guys. This is the derivative if we use the data points. Do you see that? So recommendation, always when you do economics, guys, first find the function. Once you have find the function, take the derivative, and then you have the correct derivatives. Got it? Don't try to use the data directly. If you use the data directly, guys, you're gonna find a function that looks like that. This is my marginal utility. My marginal utility is changing in different points. Why? Because my data changes all the time. My data is not precise data, so let me do this. Do you see? My data goes up, 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 down, up, very strongly up, down, down, up. And so you see, versus the smooth function here, the data has a lot of volatility. And this lot of volatility confuses the models and the results, guys. Okay. Recommendation always, smooth a function. So basically find the mathematical function, and then you take the derivatives. Okay, so that's why at the beginning of the class, I show you polyval and I show you polyder. There are two crucial variables, two crucial commands that we're gonna be using. Okay, questions? Questions, guys? No questions? Okay, so let me check if I have your homework 7.
No.
Perfect. So let me open your homework 7. That is the last homework. And I will talk about what is this. This is the last homework / project. Okay. So the 7 assignment, guys, is simply look for any economic, mathematical, finance model that you want to work with. If you are doing, if you are IT guys, you can have any model that you can imagine, but you need to apply that into MATLAB only. But I will show you how to do this in a very straightforward way. Okay, so this is going to be the assignment, the last assignment. The due date for this is going to be next Monday. Okay, next Monday is your due date. Please, Monday before noon. Okay, noon maximum. I need to grade. I need to put the grades on the system. Now, what I will do now, guys, is I will show you a couple of economic models, what I expect from you. And then next Wednesday, we have half of the class is class, and the other half is going to be another video that is a symbolic mathematics. And then you're going to have, the first beginning is I will give you a couple of more examples. Then what I want from you guys is I will invest, let's say 5 minutes with each of you. What I want from you is telling me what ideas do you have. It is not necessarily what you're going to be doing by Monday, but at least some ideas. Hey, professor, I have this paper. I work with a professor, blah, blah, blah. I would love to test it. And it is an economic model. It's a financial model, or it's a IT-related model, whatever you can imagine, okay? Just briefly, you tell me, this is my idea, I would love to do this stuff. And I will tell you, yeah, go ahead. Or, it's too complex, better do something simple. Or it's too simple, do something complex. Got it? So now let's start talking about what we can do in MATLAB, guys. If you know how to read programs, sorry, what is this stuff? What is my MATLAB? If you know how to read programs, guys, that's what I've been trying to give you. I was trying to give you functions that I created that you can read and you can modify it, and you can do whatever you want with the function. Got it? And that's what matters to me. So what matters to me in part of your project is going to be two things. The project will have two pieces. Let me save this one here, please. This is integration, integrals, and so this is so your project, guys, is going to have, well, you're going to do a couple of things. So this is the final project. So your final project, guys, is going to be, first, you need to select economic, finance, IT models. Okay. The first part, you need to describe in detail the model. So this includes, guys, that you're going to give an explanation of the model, a description. You're going to have all the equations, all relevant equations, etc. So you need to tell us what the model is about, why it's useful, when it's used, etc. And then finally, your MATLAB model. And here apply as much as you can. Apply everything that you have learned. graphs, subplots, optimization, etc. I will give you a lot of examples, guys. Don't stress with this stuff. Okay? And that's it. So the deadline is what is Monday? Monday 30, 6:30, 25, 12 p.m. via email. Okay. And then you need to have, please, guys. Oh, yeah, this is your thing. I have received a lot of your assignments with a PDF. It's very hard for me to copy PDF, directly go to MATLAB. Please, the format should be doc, a Word document that I can edit, I can copy paste very quickly. And of course, the M files and other files that we will do, MLAPP, that I will show you later today. So that's what I need. I need a doc document that I can edit, copy, paste, etc. And I need the M files and M labs. Now, also, if you use data, please provide the data, XLS or XLSB, whatever you want, but provide me the data. Okay, so you need to provide me data here. Make sense? Questions about the final?
No. And then to Wednesday, we're gonna have this time to like discuss our ideas.
Yes. So we're going to have the first part is going to continue. I will give you another model and I will show you how to create models. You're going to see. Got it?
Okay.
And then once I do this, this is going to be 30, 40 minutes maximum. Then I will have 5 minutes with each of you. You can stay. Everyone can stay. And it can be good also for everyone to listen to ideas of your friends and discuss a little your ideas. And then that's it. And then you're going to have another video of 2 hours that you need to watch. Yeah, no, I think it's 1 hour and a half. It's symbolic mathematics. And then after that, you have your time until Monday to do your assignment. Okay. But I will show you guys, it's amazingly, yeah, I would say amazingly easy to do your own models. I will show you how. Okay. But the thing is that you need to know how to read the models. Everything that we have done up to now, guys, is to learn in the language. Do you agree? The commands, the way that the MATLAB works, the way you create your M files, etc., etc., etc. So that's crucial for me, for you to understand. Once you understand that, you can do whatever you want, guys. You're gonna see. Okay, questions. So I can continue moving here. Clear? Can you open your file that says, I think it's let me close some of them. I have so many. Yeah, can you open your Cobb-Douglas function, guys? Let's open I think I gave you 3 Cobb-Douglas, right? Can you open this one here, my Cobb-Douglas? Okay, guys, are you with me?
Yeah.
Do you have this one here? Okay, so let me give you the intuition of the model. Okay, so remember, guys, we have been talking about utility functions. So when I told you, hey, guys, imagine that I have a utility and I have only 2 goods or 2 baskets of goods. I have utility X and Y, two baskets of goods or 2 products if you want. Right? What I showed you 1 minute ago in terms of utility function is that if this is X, this is the utility of X, and you see Y with a small bar. So what is the meaning of this y with a small bar? Is simply keeping y constant. So this is the utility that x is given to me, keeping y constant. So normally, guys, the utility function, as I told you, looks like that. Got it? Now, if you do the same, but I will do now a 3D graph. So now I have here y. Y also has its own utility function. So if you just take a look to these phases now, utility of, so now I will do utility of y given x constant. So this part here. So this is going to be something like that. Agree with me, guys? Do you understand what I'm doing? So for example, this is the utility of apples. This is the utility of bananas. Got it? The more I eat, sorry, when I don't have apples, I really want apples. If I start eating apples, the utility of apples goes up. But you know, this goes at a decreasing rate. So the marginal utility is decreasing. The same, if these are bananas, I just forget about apples, just focus on bananas. I know that bananas give me a level of utility, okay? Considering the apples constant. Make sense to you? So the red one is only bananas, the utility of bananas, ignoring basically the apples. And the black line is utility of apples, ignoring bananas. But you know what? That in real life, guys, the utilities are there, right? You have two apples and one banana. What is the utility that you feel with that? Well, perhaps I don't like too many apples. I like more bananas, you know? So that type of relationships implies that you are looking for these two things at the same time. So what you do is, what we're going to be doing is, we normally talk about, this looks like a dome, guys. You know, the churches, all our churches have the top of the churches have like that. It's a dome. I think you write this way, a dome. Do you agree with that? Make sense to you guys? So if you see this part here, and this part here, these are creating basically this part of the dome, a piece of the dome. Make sense? And what I do here is I can take levels. Do you agree, guys? I can do levels of this one here. So this is this line here. This line here. So basically, guys, if I reflect this line here, all this line here, I reflect this in the XY axis. So if I reflect this on here, so what I have is something like this. Do you agree with me or not, guys? Well, my graph is not beautiful, but do you agree with me or not?
Yeah.
Okay, so how do we call these ones here? These ones here are called indifference curves. So now what I will do, guys, for you is the following. I will just take X and Y. I will move X and Y into more something like that. So this is my X, this is my Y, and my indifference curve looks like that. Do you agree, guys? I've simply moved the axis. Agree with me? So what is the idea of this X and Y? Is that any of these points provide me with the same level of utility. Do you agree with me or not? Take a look. This is a reflection of this green here. This green here provides me the same level. Every point here provides me the same level of utility because I am at the same line. Do you agree? It's like being here. Every point here, okay, it's a little curve here. Every point here keeps me in the same level. Do you agree, guys? If I do this, all the dome, I'm in the same level. Let's say, if I'm talking about 2 meters, it's 2 meters here. It's 2 meters here. It's 2 meters everywhere. So you're talking about the same level of utility, correct, guys? So this line here, reflected in the indifference curve, provide me all the combinations of y and x that give you the same level of utility. Do you understand that, guys? I know most of you are not economists, but you make that this makes sense to you.
Yes.
Okay, so basically eating 2 apples and 3 bananas for you is going to be exactly the same as eating, for example, 4 apples and 2 bananas. Now, from here, what is crucial, guys, is that the value of the good that you have the least is extremely positive, extremely high. Take a look. Imagine that I have a lot of X. So I'm here. Oh, sorry. It's not a good one. Do you see that moving from X1 to X2 implies that I will have a lot of X, a lot of the good X, a lot of apples? As soon as you have too many apples now, you're going to be willing to sacrifice very little bananas. And it makes sense to you, right? Because you are so abundant in apples, but you also like bananas. So you don't want to disappear bananas. So that's why the change between X1 to X2 is large, but the change between Y1 and Y2 is small. Got it? So that's what is called, the changes here is called the marginal rate of substitution Y and X. Marginal rate of substitution. So basically means how many of X I want to sacrifice. Sorry, how many of Y I want to sacrifice for getting a little more of X. Make sense? Now, tell me one thing, guys. Take a look here in this line here. Which one is preferred for you? The green or the orange? Which one gives you more utility? The green or the orange? Oh, guys, which one?
The green?
No, take a look. The green is a reflection of this green here. Do you agree? So is this part here. The orange is more or less like here. So this
Yeah.
implies that the orange should be here.
Right.
Do you agree? So the farther you move here, the better. It's giving you more utility, correct? So
Yes.
if I do this in this graph here, so this implies that this is the case. So if you go from here to here, you are much better. You're improving your utility. Make sense? So every one of us, guys, is like saying here, guys, look, I started with 2 bananas and 2 apples and 4 bananas. But now if I have this orange curve, so basically what I can have for the same 2 apples, I can have 8 bananas. Do you see that? So where do you feel better? More is better, right?
Yeah.
Okay, so that's the idea of indifference curves. Indifference curves means that you're gonna be better in terms of utility moving from below to up, because what you're doing here, you're escalating your dome. You're moving from this part here to this part here. Got it? Now, unfortunately, guys, we cannot go infinitely because in theory we can continue going up, going up, going up, going up, going up. We cannot do that in real life. Why? Why we cannot improve our utility indefinitely? Because we have something that is called a budget. We have a restriction. So what is my restriction? My restriction is given by my budget line. So what is my budget line? It's simply like quantity of X times its price plus quantity of Y times its price should be equal to my income. Okay, I will use equal, guys, not savings at this point. Everything that I earn, I spend either on X or on Y. Do you agree, guys? So this is my restriction. So if I have a utility function, if I started here, can I improve my utility, yes or no? I start here. This is my utility 0. Can I improve or not? Guys, improving means what? Moving to the right, correct?
Yeah.
Yes, so I can improve it. So let's assume I move to this point here. Sorry, indifference curve is not you. This is indifference curve 0. Now, do you feel better in indifference curve number 1? So you have moved from here to here. Do you feel better?
Yeah.
Yes, but can you feel even better?
Yes.
Yes. So what you're going to be doing, guys, is you're going to be moving this line up to one point, up to a point in which your indifference curve is tangent to your budget line. This is the maximum that you can do based on your utility function and your budget. So this is your optimal. This is your optimal consumption, your optimal X and Y. If you have, enough money to buy 4 apples and 4 bananas, that's your optimal. Make sense? Some other individuals are going to have the budget is going to be either to the left or either to the right, and this depends in individual. That's individual based. Make sense to you guys?
Yeah.
Okay, so let me save this one here. Okay, so what I will do, the Cobb-Douglas, guys, is a function. It's a very particular way of function. So this is my Cobb-Douglas now. It's a very interesting function, Douglas. It has a lot of properties, guys. Okay, that I will not go over them. But the thing is the following. So my Cobb-Douglas, this u of x comma y is going to be simply equal to x to the alpha, y to the 1 minus alpha. And what is alpha? Is a proportion of budget used to buy x. In such a way that, of course, alpha plus 1 minus alpha equals 1, right? So you spend all your budget on these two, x and y. And my restriction is going to be subject to, I cannot spend more than my income on these two baskets. So this is my optimization, guys. This is what I want to use. I want you to tell me what is my utility. Okay. In the model that we are going to be seeing, guys, I will assume alpha is 0.5. Okay. If alpha is 0.5, I want you to tell me how much you're going to consume from X and how much you're going to consume from Y. That's what we want. Or for a given I. Okay. So I will give you I. If your income is 100, the price of X, I need to give you P of X, I need to give you P of Y. If the prices are this and this is your utility function. So this is the way you are defined. So with this utility, guys, you create the graph that I created here on top. So one way of solving this equation, guys, and that's the first one that I present in your MATLAB, Cobb-Douglas number 1, is how do I solve this one here? This is a restricted optimization. Do you agree? Why is restricted? Because I have a limit. But I can transform this restricted optimization in an unrestricted optimization. It's a kind of unrestricted, but it's indeed restricted. You're going to see the following. Tell me one thing, guys. I will take y out of, so let's say this is 1, this is 2. Just working from 2. tell me if this is right. I want to take y out. So y is going to be equal to I minus xpx divided by py. Agree with me or not? Using 2.
Yeah.
Yes. And then what I will do is I will do 3 in 1. So I will disappear this second equation. So my utility also is going to be equal to x to the alpha. Y is all this part here. I minus xpx over py to the 1 minus alpha. So this is going to be my function. And I will work with this function to find x and to find y. Where's my, oh, so y later. Y using this equation here. Make sense to you? So I will give you, guys, you're an individual that has a Cobb-Douglas utility function. So a Cobb-Douglas utility function looks like that. We are going to graph this later. Looks like that. Imagine that you have your income is going to be this much of money. The prices are these prices. So tell me what is going to be your optimal consumption on X and your optimal consumption on Y. Okay? So that's what you have in your MATLAB code. Let's say 4 minutes, guys, for you to analyze the code, understand what the code does, run line by line, and that's it. Okay? 3-4 minutes to do this. One minute, guys. Okay, guys. Make sense to you? So my parameter alpha, 0.5. So basically implies that I will have a 0.5 for product X, my prices, and my income. And this is the way I want you to do your models, guys. I want you to have your equations if it's possible, because sometimes some economics or financial models don't have a closed-end equations or solutions. But this is the one that we have done. So my utility My variable is going to be x, so that's why it's called x. And oh yes, why I'm using the minus here, guys? Because remember, the functions always look for minimums. They don't look for maximums. So that's why I need to have the negative value. This is x, it's called x1, this is a variable name, to the alpha times I minus px times x1 divided by py to the power 1 minus alpha. Agree, guys? So basically, this is this function here. This one here. Agree with me? And then what I will do is I will do an initial guess. I will say that, you know what, my x0 equals 10. Yes, as a guess. And then I will do what is my optimal x. Okay, my function is utility, is this function here. I know that what we want to optimize is on x. And I give a starting value. X equals 0. Sorry, x0, 10. My starting value is equal to 10. Once I find this value here, guys, what I will do is I will use this value to compute my y. So I'm using this equation here. I know now what is x. I know, of course, I, px, py. And I simply replace this one here, and I find my y star. This is my optimal y. And then I simply print my results. You can see this is f print f. This is what is going to appear. It's optimal x, two decimals. Optimal x, print my optimal x, print my optimal this one here, and give me the utility value. So once you have x and y, guys, once you have x and y, you can replace in here. Do you agree? X, you know alpha, y, you know y, and you know 1 minus alpha, and you give me the value. So what is the level of utility that you are obtaining given this income? Okay, so basically, what is this level here? Oh, sorry, what is this one here? Make sense to you guys? So we can run. You just run this program. And let me move this a little here. Here we go. So with this budget, with this utility function, you're going to obtain the maximum utility when x is 25, your y is 50, and what is the level of utility that you're obtaining? 35.36. Make sense to you guys? Make sense or not?
Yeah.
Perfect. Now, can you please analyze the Cobb-Douglas number 2? You have also this one here. The only thing that I'm doing here is adding plots. Take a look. Two minutes to understand what we're doing. It's very, very similar to the one that we have checked now. Okay. So the only thing, guys, that we are doing is simply creating a plot, and you're gonna see how interesting is this graph now. Go here. Guys, do you see that? My utility function. So this is in terms of x. When x is 25, my utility function is going to be 35.35 Makes sense to you? So this is exactly what we were graphing here in a univariate model. Well, this one here. This one here.
Professor,
Yes.
question.
Yes, go ahead.
Can we also plot the different lines like when we move to the optimal utility function?
Yeah, you can, definitely. And this is going to be part of your assignments. Yeah, you're reading my mind. Yes.
Okay.
You can. You definitely can. And let me show you the last model, okay, for tonight. Can you go to Cobb Douglas number 3? So in Cobb Douglas number 3, guys, what is really interesting is that I'm using these equations, these two equations. I have my objective function and I have my constraints. So remember that for using the F-mean search, I need to have a single equation. It can have two or three variables, but it should be a single equation. But what if I have not only one restriction, I can have four restrictions. So I need to have this type of equations, a method that helps me work with this type of equations. So this is the example that I'm providing you here in what is called the F-mean con. This is a new one. Is the function minimum constraint. Okay, so 2 minutes to read this one here, please. Ready? Ready, guys? So let's run this stuff. Simply run. And here we go. Using the exact same values as it should be. The thing is that what is beautiful about this F-mean con, guys, is that you write a function. This is my objective function. X to the alpha, y to the 1 minus alpha. Subject to, I have my constraints here. My A is going to be P of X, P of Y, that I have given as data. And my B is going to be I. Okay? My lower limits, of course, I need to have a non-negative consumption, lower boundaries, 0 and 0. And my initial guess is going to be a 10 and 10. Then I will do my F-mean con, my utility 2. This is what I call. I give x0. X0 has two values here. I give my constraints, A, my metrics of prices, and B, my income. And these options are my limit boundary, etc. It's not a big issue. And then you simply run this stuff. Okay, so your assignment for next week, guys. No, next week, sorry, for next Wednesday is very straightforward. What I want from you is the following. I want you to add a graph to this one here. So you need to add a figure to this Cobb-Douglas 3. And in Cobb-Douglas 2, what I want from you guys is like your colleague is saying, oh yeah, I have this in terms of X. I want this in terms of Y. Okay, just do as many graphs as you can in graph number 2, sorry, in Cobb-Douglas number 2. And then I will show you next week, next Monday, next Wednesday, my gosh, next Wednesday, how to do an app, okay? How you want to be able to basically move the parameter. So what happens if my income increases by 10? What happens if the prices increases by 20, etc.? Okay, we're going to do this next week, so next Wednesday. Questions for now, guys? You have all the code. Please read the code. Next class, we're going to do several examples. I will show you how to do that. Then I will show you how to create your programs in a very easy way. Very easy, but I will show you also how many problems you can have with that and how many tricks you do in order to find a final solution to your models. Make sense?
Yeah.
Okay. So that's it for today, guys. So we see you in. I will send you the video that you need to watch tomorrow early in the morning, so you can go and start looking for. From it's 1.5 hours that you need to watch. Also, it's another video that deals with something we're going to be using in the next class. Okay.
Okay, thank you.
Okay, guys. See you. Good night. Have a good night.
Thank
Good
you.
night. Thank
Take
you.
care. Bye, guys. Bye bye.